program. Our next speaker is Geoffrey McLachlan from the Department of the University of Queensland, and this will be a more statistically oriented program.
Good. Thanks, Peter, and thanks for the invitation to speak here this afternoon. Yeah, it is. You've been forewarned by Peter that it is going to be a statistical talk. I'm a statistician with really no background in biology, although I have a joint appointment now with the Institute for Molecular Bioscience. The references on my work, you can, if you're interested in, they're given on my homepage here, and all the papers can be downloaded, and inside those you'll see the references to other people's work. Although obviously you can't reference everyone in bioinformatics, the field is so huge. Well, yeah, so I'm concerned with the statistical analysis of microarray gene expression data, and the output, if you've got, say, M microarray experiments, you can represent the output in this capital M by M array. Each column here refers to the output from a single microarray, and then the rows are the expression levels on the genes. And so we have, say, for a given row we've got the gene profile, and for a given column we've got the signature, and of course, as you know, the number of tissue samples is generally limited, mostly in the order of 100, whereas the number of genes can be quite large. And so this is just a general statement about the statistical analysis of microarray data present quite a number of challenges, in particular because we've got very little replication, lots of genes, and only a limited number of tissues. Now, I'm going to be talking about probably a fairly simple problem today, and that's the detection of differential expression. I'll give a definition of that shortly, but I thought before I got into that topic, I'd link it up with two other things in associated things. One is the supervised clustering of tissue samples, and the other one is the clustering of gene profiles. So you can also approach this problem by actually clustering the genes, and I'll say something about that at the end of the talk. So what do we mean by the detection of differential expression? Well, of course, all biologists would know what we mean. We've got a number of classes. I've just got the simplest case here, 2 classes, and for a given gene, we're interested in seeing whether it is behaving differently in the 2 classes. So the null hypothesis is quite clear, and that is the gene's got the same behaviour in both classes. The alternative, well, in its most general form, it would be that the gene is behaving differently, but generally speaking, we use a test statistic that looks for a difference in mean. So if we've got 2 classes, we could use like the simple t-test. If we had more than 2 classes, we may use, say, an f-test from an ANOVA. And I'm going to sort of basically just focus on one small data set that's been analysed quite extensively in the literature. This is the head and fork breast cancer data set. It's a very small data set. You've got 7 females with this BRCA1 gene and 8 with the BRCA2. And the problem, there's 3,226 genes, and the problem is to find which genes are differentially expressed between between BRCA1 and BRCA2. And this is a reference to the data. So for people who've been working in this area, this data set's been analysed very extensively. So I've called this gene J. I don't know actually what gene it was. So the data's been normalised. I should say, underlying all this is basically the data's been normalised. So we don't have to assume, but probably the data would be. It's reasonable to take the data to be normally distributed in each class. But that's not essential for what we're doing here. So here's a particular gene. We've got these 7 measurements, and then we've got 8 measurements in here. So this is like an exercise in the first few weeks of statistics. You've got your sample mean and the sample variance in each class. You may want to pool the sample variances, and then of course you've got your 2 sample t-statistic, and it comes out to be minus 0.6. So you work out the p-value, assuming that this has got a t-distribution with 13 degrees of freedom, and we get a p-value of 0.5. And of course, if we don't, if we're a bit worried about using the t-distribution there, we could use a permutation test or something like that. So I'm going to so that's the problem I'm going to be talking about. And of course, for a given gene, this is quite a simple problem. We've just done it. We just used say a t-test here, and but we've got lots of genes here, 3,226 genes, which we want to simultaneously test, and so that's where the difficulty comes in. So, but before I get into that, let's look at the supervised classification problem. We've got, say, two classes again. So this may be, again, thinking of females with breast cancer. This class may be patients who are thought to have good prognosis. That is, they'll go 5 years without, they'll remain metastasis-free for 5 years. And this poor prognosis class, people may, metastases will appear in 5 years. And we want to try, and so a new patient presents herself, and we want to try and predict whether the person should be in this class or that class. Or maybe these classes refer to the course of treatment, whether some person should get chemotherapy or whether they should not. And some statisticians have said maybe we shouldn't be worried about differential expression. We should be focusing more on this problem, trying to find genes that marker genes for these two classes. And so the thing I just wanted to mention in part is the selection bias. And because we've got so many genes to choose from, that if you go ahead and form a classifier using some method of gene selection, then you have to be careful that you take into account that you selected the genes in some optimal way. And now, statisticians have known for years that there's a selection bias, and when I wrote my book a few years ago now, I've had a section on it, sort of surveying the results done many years ago. And Leo Bryman, or the late Leo Bryman, wearing his machine learning cap, I think he liked to keep statisticians honest. He mentioned here that it's long been a quite scandal in the statistical community in this context. But I think the reason why it's been a quite scandal is that in statistics in the past, we've never had many variables anyway, so the selection bias, even though it may have been there, it's never been very large. But of course, when we've got so many genes now to pick from, the selection bias can be quite large. And what drew my attention to it was I was trying to build a classifier, and I was using a support vector machine, which Vapnik had developed originally. And in this particular paper with Isabelle Guon, they developed a support vector where they used this method of selecting the genes called recursive feature elimination. So they fitted the support vector machine to all the genes using a linear kernel, and so they ranked the genes on the basis of the magnitude of the coefficient of that gene, and then they threw away the genes that were lowly ranked. And they did this in chunks of a half, so they kept throwing away the bottom half of the genes. And they said that, and they got these results that they came up with a classifier based on only 1 or 2 genes that had a 0 cross-validated error rate. And they did realise something was going on, but they said the success of the RFE indicates that it has a built-in regularisation mechanism that we do not understand yet that prevents overfitting. Well, but it didn't prevent overfitting. And so just briefly looking here, this diagram you should read from right to left. They fitted their support vector machine to this colon cancer data. It's from the Allen et al. Paper, which is another data set that's been analysed to death. But so this has got 2,000 genes. Then they started to throw away the genes, so the error rate comes down and then goes basically to 0, and then starts to go up again. But they didn't take into account this selection bias. So when they try to estimate, say, the number of genes here, at 2 to the 6, say, 64 genes, they use those same 64 genes at each stage. Whereas what they should have done when they did their cross-validation was to go back from the start and have a look at it and select the 64 genes again, which may not be the same as the original. And so this is the true error rate. This solid line here was an estimate. So the error rate is not 0. It's more like at least 17%. So yeah, so the so that sort of caught our attention, and Christoph is here today. So we wrote this paper, and but other people had realised this selection bias, and of course this is not the only paper. There's still, you pick up a paper, and when you see it's on the colon cancer data set, and they're getting 0 error rate, you know that they've made this mistake. Now, and of course, some people have written on this, and some people have really got quite taken it. They've got here, it's a threat to the validity of cancer molecular marker research, the bias. But now, this selection bias is present in all types of forms. There's a famous data set on breast cancer by Lara Van Veer, and she selected the top 70 genes essentially on the basis of the T statistic. She didn't say that. She talked about a correlation between a class label and the expression level. But basically, she picked out the top 70 genes, and of course, she's selling those genes now to people, those top 70 genes. And but if you just make those, if they only list 70 genes, and you take your favourite classifier and run it on it, so here, this is just taking the top 70 genes in terms of the T statistic. If you fit a support vector machine to that, it looks as if it's doing pretty well, because the error rate is essentially about 20%. The smallest value there is about 90%. But if you go back to all the genes, well, these aren't all the genes, but there's been a lot of genes and they've been filtered out. If you fit a support vector machine to those genes using recursive feature elimination, you can see about the best you can do is about 29% there. Well, the lowest value here is about 29, which is greater than here. And in this column here, you can actually correct for the bias, but to correct for the bias, you need to have all the genes. So there's a danger in people make only a limited subset of the genes available, because basically you can't get an unbiased assessment of a classifier on it. There's also another bias here. If you run, say, a support vector machine on these genes, and you look and you go up here and you say, oh, okay, I got a 29% there. This one looks a bit unusual too here, being that low compared to its neighbours. There's a bias there in picking out the smallest number. So you really need to do another layer of cross-validation. And when you do that, the correct for bias, the error rate comes out to be 37%. So basically, the best you can do at the starter set, well, this is an estimate, is saying that it's got an error rate of about 37%. So that's quite high, given that these 70 genes have now been. So these 70 genes, this kit, if you like, has been approved by the FDA. I should say there's been lots of papers written. People have come up with another lot of 70 genes that do just as well as the ones that Lara Van Veer put forward. I think before this was actually approved, they went out and took another 234 tissue samples, breast cancer samples, and I should say these are based on 78 tissue samples. So they took 61 of those 78 and got an extra 234. So they had 295 tissue samples now. But although they knew the true outcomes for most of the patients, some patients died so they didn't know the true outcomes. They actually predicted the outcomes using the original 61 tissue samples. So to me it seems quite bizarre really that you know the true class labels, that is these women were followed for 5 years and they know whether they had developed metastases or not, but they ignored that and predicted whether they would fall into those two classes and use those predicted labels to build their discriminative function. And when you do that, they got an error rate of about 14%. But basically, if you use the true class labels, the error rate's more like 28%, 30%. So again, even with these additional tissues samples, the error rate's still about 30%. Anyway, last year, on the 2nd of July, the FDA approved this kit that they sell, MammaPrint, and it was it's the first cleared product that profiles genetic activity. So in a way, I suppose it's good that attention's been focused on the possible potential of these gene expression levels to help in the diagnosis of these diseases. But to me, it seems, without knowing too much about this, rather premature on the basis of these two data sets. But at the same time, they are conducting a big trial that's going on, and I don't think that's going to be completed till 2010. So anyway, I've written a little bit about this in a paper this year in the Journal of Statistical Planning and Inference. And this book, this fellowship in honour of P.K. Sen will be out in 4 weeks' time, and I have a chapter in that on this. So that's supervised clustering. The other thing is supervised classification, I should have said really. And the other thing now is the clustering of the gene profiles. The previous speaker was talking about clustering gene profiles, looking at time course data, and you can do that using what I'm going to describe shortly. So with the microarray data, there's really two clustering problems here. You can try and cluster the tissue samples, and so you've got little n here is the number of tissue samples, which is generally quite small, relative to the number of variables, the genes, which is capital N. And this is a problem I looked at some time ago, but it's not really related to differential expression, so I won't go into it now. I had a program for some time now called EM, that's the expectation maximization algorithm. So this MMIX stands for EM mixture analysis. And in this modified form for lots of variables, I called it MX gene. But then later on, I wanted to cluster the genes. So in a way, that was a bad choice. They're putting a gene there when I really was clustering the tissue samples. So anyway, I call this procedure MX wire. I suppose another terrible name. But so it stands for with random effects here, the WI. And basically, I think the biologists are more, well, there's lots of biologists here. You can correct me if I'm wrong anyway. I think they're more interested in clustering the genes rather than the tissue samples. And so we might want to cluster longitudinal data. We could have with or without replication, or we could have cross-sectional data. So in the detection of differential expression, we've got cross-sectional data because we've got different classes. And this came out last year, or 2 years ago now, in a paper in bioinformatics. And basically, we fit a mixture of linear mixed models. We've got these fixed effects terms here. So in what the last speaker was talking about, time course data, you could have a sinusoidal curve here by putting in a sine and cosine functions in there. But we've got these random effects terms, and this random effect term here is to allow for correlations between the replications on the same gene. And this random effect term here, associated with a cluster, it enables the genes that are put in the same cluster to be correlated. So genes that are in the same correlated are supposed to have the same covariances between them. So that makes some attempt to take into account that the genes aren't all independently distributed. So the presence of this term increases the degree of difficulty of the analysis. You can't write down the likelihood for it in closed form, but of course if you use the EM algorithm, you can declare these random effects to be missing data, and you can write down a complete data log likelihood function. So if there's time at the end, I'll come back and say more about this. But it does offer a way of looking at the detection of differential expression. And for example, with the head and fork data, we could set this up. We've got two classes, so we could set up our X matrix to be this. So these are the 7 observations in the first class, and these are the 8 in the other. And basically, we end up actually clustering the genes into only 3 clusters. In one cluster, these betas are roughly the same. In the other one, this beta is greater than that. That is, the gene is upregulated in class 1 and down in class 2. And in the other cluster, it's downregulated in class 1 compared to class 2. You might wonder why there's not more clusters, but we actually normalize the rows, which does constrain things. So you end up basically always getting just about 3 clusters. If you're interested in reading about clustering, there's a few books coming out in bioinformatics, and I have, with some colleagues, we've got some papers on clustering in those books. So back to the original problem, we've got this 2 classes. We're trying to work out which genes are differentially expressed. And so this is what happens with a particular gene. We work out a p-value. So all we need is a p-value. So you can use your favourite test to get the p-value. I've just used the t-statistic here, the 2-sample t-statistic, but you could use a moderated form of the t-statistic where you allow for the fact that you're going to share some of the sample variances. So you might be worried about a sample variance that is almost 0, giving you a significant result. But whatever, we just need a p-value to proceed. So it's up to the person to provide the test statistic. And now, I say, if you don't want to use the t-distribution, we could use permute the class labels for a given gene. If there's not enough tissue samples, and that'll give too granular an estimate, so we can pool over the genes. So anyway, the reason why we're talking about this problem is that instead of just having one gene, we've got lots of genes, so it raises the problem, what do we do? We could use the Bonferroni method if we only had a limited number of hypotheses and control the family-wise error rate. But given how many genes we've got, that's too strict. And so thanks to Professor Benemini here, we've got the false discovery rate to look at. And that's basically what people tend to use in this problem, because we decide to look at the number of false positives, if you like, among the genes declared to be differentially expressed. So we can think of the false discovery rate basically as being the number of false positives among the genes declared to be differentially expressed, or the non-null genes. And the false non-discovery rate is this ratio, although because A is very large, this quantity can be very small, even though you might be doing very badly. So it's probably better to use the false negative rate, this quantity here. So besides monitoring this false discovery rate, you should really, I think, monitor some other error rate like the false negative rate. And of course, these are only empirical definitions. The actual definition is given by the expectation of this ratio, where this notation means you're taking the maximum of that quantity in 1 to handle the case where this is 0. Now, okay, so we've got our p-value. And if we're going to use the t-statistic, this is how we compute the p-value. Now, Efron converts his p-value to a z-score. So rather than, people like David Allison have worked at these p-values on the unit interval and have fitted mixtures of beta distributions, but I think it makes more sense to work on the real line. So this is Efron's using the Probit transformation basically, and our transformation is this: we only want to fit a two-component normal mixture model. So basically, this is our transformation here. We want large values of the z-score or the z-score for people from America to reflect differentially expressed genes. Whereas with Efron's transformation, you've got genes with large values of z, j, or with large negative values. So this way, we've only got null genes will have values of this consistent with a standard normal, and genes that are differentially expressed will have large positive values of that. So, so Lee and Efron and others, Michael Newton, have looked at this definition of a local false discovery rate, where you model the density of the test statistic, which is our z-score. Basically, we've gone from a test statistic to a p-value to a z-score by this two-component normal mixture model. Pi sub naught here is the proportion of genes that are not differentially expressed, that is the null genes, and this is the density. And F sub 1 is our density for genes that are differentially expressed for the z-score. And then if we use Bayes' theorem, we can write this, I'm calling this probability, this posterior probability, tau sub naught. So it's the probability that the Jaf gene is null given a value for its z-score. So if we hadn't observed the z-score, then this would be pi naught. Having observed the z-score, we modify pi naught, and we just got this posterior probability here. So the FDR is a global measure. It's associated with the average number of false positives, whereas the local FDR focuses on, for a particular gene, the probability that it's differentially expressed. And if you use this mixture model approach, you can also get estimates for the local FDR as well as the global FDR and other error rates such as the false negative rate. But as I say, this is a simple method, and it's basically in this paper here in bioinformatics. I should say, in doing this work, I've drawn heavily on the work of Brad Efron. I like reading his papers. There's always something in them, and I haven't got all of them down here. I think there's a few more, but if you go to his website, he's got these papers here. Some of them have been published, others are coming out. I think there's one in Statistical Science, another in the Annals of Stats. And this is just an example of the local false discovery rate. So this is from Gary Glonick and Paddy Solomon, fellow Australians, in discussing a paper by Terry Speed. And so here we've got our z-score. Its null distribution is the standard normal. And we're supposing that its alternative distribution is a normal 1,1 and that pi naught is 0.9. And suppose we're going to declare genes to be differentially expressed if their z-scores greater than 2. Now, if you work out what tau naught 2 is, that's the posterior probability that it's a null gene given that z equals 2. It basically comes out to be 1. But the false discovery rate is 0.17. So the green curve is the standard normal weighted by 0.9. And if you get a value of 2 here, you can be pretty confident it's going to be a null gene. But even if you declare it to be a differentially expressed, the false discovery rate's about 17%. Now, if you just modify that 0.9 to 0.6, let it drop to 0.6, the false discovery rate remains the same because it's concerned with what happens on average. But the local false discovery rate, that is this posterior probability now for a gene that's got a z-score of 2, drops to 0.251. So the local false discovery rate is sensitive to what's happening for a particular gene, whereas the FDR is a global rate concerned what's happening on average. So the procedure, as I say, is quite simple. We've got a test statistic which gives us a p-value, which we convert to a z-score, and then we rank the genes on the basis of these z-scores, and then we work out these posterior probabilities, and then we declare a gene to be differentially expressed if its estimated local FDR is less than some constant C0. And if you want to link this up with the Bayes risk, it's equivalent to minimising this particular quantity here, where these are the two types of error rates. So okay, so basically Efron estimates this local FDR using non-parametric methods, but I'm going to proceed now just fitting mixtures of normals to do it parametrically. So we want to estimate this particular quantity here. So we've got to try and make this problem identifiable. Well, it's reasonable to take this null density to be a normal 0.1. So if the p-value, if we're confident that the p-value is going to behave as a uniform random variable under the null, then this z value here will be a standard normal. So its density is a standard normal. We can estimate the whole denominator here pretty easily just from all the z-scores, but in order to make this problem identifiable, we've got to put forward some candidate for this density here, and basically we can get away with, it seems, with just using the a single normal distribution. So we're going to well, this old, if you like, this is the non-null density of a z-score, and any density of a continuous random variable can be modelled by a mixture of enough normals. If you take enough components in your mixture model, but it turns out for all the data sets we've looked at, you can get away with just a single normal distribution there. These are some simulations. If you had a non-null gene, well, this is what happens in the null case, but if all the genes had the same mean relative to the standard deviation of 1, they'd look like this, a normal. If they had the same value 2, 3, so you might think, well, you really need a mixture of normals to cover the genes because they don't all have to be expressed to the same difference. But it turns out in practice we can get away with just having one non-null normal density. So I've got a program called MXFDR. The MX seems to precede everything here. So what we want to do now is to fit this two-component normal mixture model by maximum likelihood, because this is reflecting the null genes and this is the non-null genes. And we can do this very quickly because when you write down the maximum likelihood estimates for these parameters, they satisfy these moment equations. And so basically, if you know what pi naught hat is, then sigma 1 hat squared and mu 1 hat are given automatically. So basically there's really only the one unknown parameter you've got to estimate, a crucial parameter, pi sub naught, because once pi sub naught is known, the others come out. And so basically, to run the EM algorithm, you've just got to give it a value of pi naught, and then you just you just look at values of pi naught in a range. If you want to speed things up, you can get a good idea what the value of pi naught must be if you go to the left-hand side of the histogram of the z-scores, because on the left-hand side it should be behaving like a standard normal weighted by pi naught. So if you go far enough out and take the area to the left of that point, that should be roughly the area under a standard normal weighted by pi naught. So you can get a good idea what pi naught should be. And you can estimate these. So having fitted the normal mixture model now, you can estimate these other error rates. This is, say, the false discovery rate. So this is just the estimated posterior probability for a gene with this z-score, the Jth gene, and this is the indicator function here that takes the value 1 if its argument falls in that interval there. So you just got to add up over all genes and divide by the number that are rejected. A gene gets declared to be a non-null gene if the value for this estimated local FDR is less than some C0. And similarly, you can estimate these other things like the false positive rate and the false non-discovery rate and the false negative rate. So once we've fitted the mixture model, you can estimate these error rates. And so here's our histogram of these z-scores, and so if we go ahead and fit our two-component mixture model, the green curve is the standard normal weighted by pi naught, and then the blue curve, the red curve is the normal component corresponding to the genes that are differentially expressed, weighted by 1 minus pi naught, and there's our overall mixture density, which is doing a pretty good job. If it wasn't providing a good fit, then you could add some more components on there. So, okay, in the this particular example, we rank the genes having from smallest to largest according to their value of the local false discovery rate. For the head and fork data, the smallest value we got for this was 0.01. There's really a bias there also, because we've picked out, this is the smallest of 3,226 genes. If we did the experiment again, the value for this particular gene, whatever it is, it would have a value larger than what this is here. But you can do a cross-validation exercise to raise that estimate if you wanted. So anyway, suppose we actually drew a line under all genes which had a value of the local false discovery rate less than 0.1. I'm not suggesting you would do that in practice if you could see this small difference here. But then 143 genes would be declared to be differentially expressed because they've got this value of the local false discovery rate less than 0.1. Now we might be, so if we do that, so this is the local false discovery rate. If we want to estimate the false discovery rate, then we would add up all these quantities here, divide by 143, and we get 0.06. There's nothing magic about trying to keep the false discovery rate at round about 0.05. It's just so happens that if you do take this C0 to be 0.1, then you get about 0.06. I think Efron tends to work with a value of this about 0.2. But now you might be interested in saying, okay, what would happen if we went down and looked at the top 200 genes, and then if you add up all these quantities here, divide by 57, and then take the answer away from 1, you'd say, okay, there's an 89% chance that we've got some false negatives here. This is the proportion of false negatives in this lot of genes here. So it's just, I suppose it depends on how much work the biologist wants to do where we draw this line, or where their favourite gene is, I suppose, just how far down the list it is. So anyway, you can draw up this table, and And you can look at what happens as you vary the value for the threshold. If you take this to be 0.1, then 143 genes are declared to be differentially expressed. The false discovery rate's estimated to be 6%, and the false negative rate is quite high, it's 88%. But to get that down, if you go to 0.2, the false discovery rate now goes to 11%, but the false negative rate jumps to 73. And so it gives you some idea that as you vary the threshold, how this error rate's going to fall, but then this other one goes up. So it's something that the user can decide. I won't dwell on this, but so we looked at what happened when we did apply it to the hidden fork data. So we got actually 143 genes declared to be differentially expressed, taking 0.1. And hidden fork themselves had 175, and Story and Tibshirani in this paper had 160. And these are the genes that we found to be differentially expressed that the others hadn't noticed, and this is their go term there. And examples, the estimate of pi naught, these are various people who've looked at this data set. We actually got a value of 0.65 here, and these are other values that people have got for the pi naught. Now, so Efron has put forward the idea of an empirical null. And the idea is that maybe we shouldn't be using the standard normal as our null distribution. And so this is taken, I was in Seattle when he gave his presentation on this talk. So this is based, this next two slides are based on his talk. And there are 4 reasons why, well, there's lots of reasons, but these are the 4 main reasons why the standard normal may not apply. That's the theoretical null. And one is you use the student t distribution where you shouldn't, but that can be corrected for because you can use permutation methods. But you could have correlations across the arrays, and the standard null density assumes independence there, and permutation methods won't help. You could have unobserved covariates, and permutation methods can't help there. And then the other reason is when you've got correlations, of course, across genes. And probably this is present in most data sets because not all the genes are independently distributed. And so for the moment, we're going to suppose that 1, 2, or 3 is applicable, but 4 is not. So we're going to assume for the moment that the genes are independent. And so we come back now to the problem of estimating the local false discovery rate. Now, instead of taking this to be a standard normal, all we do now is estimate the mean and the variance. So we've got to estimate this density here for a non-null gene, but now we're going to estimate the mean and the variance for a null gene. So it means that there's a little bit more work to do in fitting this 2-component mixture model. But again, we supply an initial value for pi naught. We then rank the genes, and we put the n pi naught smallest in one group, and then the others and then the remainder into the other component, and then work out the means and the variances if they're the true groups, and then you fit this normal mixture. And you can do a test of whether you think that the increase in the likelihood, log likelihood, warrants fitting an empirical null instead of a theoretical null. Now the fourth reason, well, if the genes are correlated, even if the distribution of a particular z-score for a null gene is a standard normal, it doesn't mean to say that the ensemble of these z-scores, these null z-scores, will behave like a random sample from a standard normal because of the correlations. So this correlation, So if we're going to use p-values based on the theoretical null, we can get into trouble no matter what procedure we use. So we still go ahead and fit our normal mixture model, although basically now it's not the true likelihood due to the correlations. And so that's what we got before when we, I don't know if you can see these curves, but that's what we got before when we had the theoretical null. And when we fit an empirical null, well, it's very hard to compare the two slides when they're not up together. But basically, it's slightly different. But the best way to see it is to look at this table here. When we use a threshold of 10%, 143 genes are declared to be differentially expressed with the theoretical null, but if we use an empirical null, we get 62. The reason why we get less genes is that the estimate of pi naught now has gone from 0.65 to 0.7 something. And if you use a threshold of 20%, the number of genes that are declared to be differentially expressed has gone from it's fallen down. It's gone from 338 to 212. So you've got this, I know where it's a problem, but although there's not much difference in the fit, in the actual curve, using the empirical null over the theoretical, it can make a difference to which genes, how many genes are declared differentially expressed. Now, this is a simulation experiment. Allison, when he looked at this problem using p-values rather than z-scores, he was generated some data for 10 tissue samples, which he called mice. And so he generated these genes to be correlated in blocks. So the genes were correlated in blocks. And we did the same experiment. And so when the correlation was 0.8 between these genes in blocks, this is what we get for the theoretical null when it tries to fit these histograms of z-scores. But if we use an empirical null, it does a much better job of trying to approximate that histogram. So it would seem that the empirical null is some way of improving things when you've got correlated genes there. In this particular case, because the genes are so widely separated, there's not much difference. So I'd like to conclude just by saying, well, how could we look at this problem using clustering? Well, I mentioned this MXY procedure before. Efron calls what we've been doing up to now he calls it working outside the X matrix. And so here, basically, we go inside it and we try and model all the data. So we have to make much stronger assumptions to do that. But if the assumptions are correct, then it's a much more powerful, you'll get a much more powerful test. And so we fit this mixture of linear mixed models. When you go to work out these posterior probabilities, you've got a condition on this cluster effect here, because basically you can't write down anything in closed form unless you condition on that cluster effect. I can't seem to... I think I've got rid of the slide I wanted to... I must have omitted the slide. I was going to show you what we get by clustering versus the head and fork data. But anyway, this is a simulated data. So naturally, we simulated some data from this mixed model, this mixture. So I mean, obviously fitting that mixed model is going to work. And so when we simulated it, we use the empirical, and this is what we get from a clustering approach. So you can see here that so if you use the empirical approach, where you just basically work with the p-values and convert them to z-scores, you'd get 32 genes declared to be differentially expressed at this threshold. But if you use this clustering approach, you get 182 genes at the same value of the FDR. But the false negative rate is much less. And similarly, when your threshold is 20%, you get 193 genes declared to be differentially expressed compared to only 80 if you just work in terms of the p-values. And of course the false negative rate is much less. So, but I mean to say, in this particular case, the data has been generated from the model that we're using to cluster it. So it's obviously, and in practice, it's always dangerous, I suppose, to be fitting these full models. So I think I like the way of working in terms of the Z-scores. Well, to finish up, this mixture model approach to finding differential expressed genes is both convenient and effective. It can be done very quickly because we only have to fit 2 normal components. And particularly with the theoretical null, once you specify pi naught, you've specified all the other estimates. It gives measures of the local false discovery rate as well as the global and other error rates. And then we can incorporate Efron's, I think, very clever idea of this empirical null for use when the theoretical null may be misleading. Good, thank you.
10 minutes, questions?
For these 2 component mixture model you presented, so for any real data, there is no reason to believe this one is really fit the data very well. So it seems to me it's kind of your assumption. So and then the original assumption is that one component is normal 0, 1. But now you relax this one, says, okay, I want to totally estimate this component. So now I'm puzzling because for original setting, I have clear interpretation. This normal 0, 1, you are estimating the false discovery rate. But now, instead, you relax this. I'm puzzling what is really the meaning of you are estimating. For example, maybe the true data has 3 or 4 component mixture, but then you relax the assumption, then I'm a little bit puzzled.
Often my students are too after a talk. If I could just go back to your initial comments, these are real data sets. In all the data sets I've looked at, basically I've only needed 2 components. But if you read up the work of Pounds, where they work with p-values and fit mixtures of betas, they've only needed a mixture of 2 betas, a beta 1,1, which is the uniform for the null genes, and then one other. Like Percy Diaconis showed that any distribution with support on 0.1 can be modelled by a mixture of betas. They've only ever used one, but found they only ever needed to use 1 beta. And in dealing with the data sets we've looked at, we've found that we've only needed to use 1 normal component here. But in the case of the theoretical null, everything's nice because we're saying, okay, the null genes are going to obey the standard normal. And so if we only need a single normal component here, then we can just go ahead and fit this too. But it wouldn't matter to the estimation of pi naught how many components we would put for the density for the non-null genes. It doesn't. It's not going to influence the.
So to form theoretically, so whether you can justify this theoretically says your estimate is a consistent estimate of this particular component. I guess that is more interesting to investigate.
Well, if you can get away with 1 normal component, it removes the problems with identifiability, because you don't want to say, okay, this one is a mixture of a normal 0.1 plus another normal, because then that would affect the estimation of pi naught. But it gives, but in most, all the data sets we've looked at, we can get away with a single normal here. So the problem, the pi naught is identifiable then from that particular problem. Now things get a little bit not as clear when you go to the empirical null, but otherwise, but I still. But there's, yeah.
There is a fifth reason that Efron doesn't measure for the same problem with the null distribution. And this is a problem that the genes expression that the statistician sees are not the gene expression that the biologist measures. In the example you gave, I think there were 6,000 genes originally, and only 4,000 appear. Now, if you read and see the reasons why they are, the way they do not appear, these are the intensity is not high enough, the things are already too close, the standard deviation is too small. In fact, those are exactly the reasons that will perturbate the distribution under the null in the place where it harms you most, and this is near zero, the place where you're trying to estimate pi naught. So it's not wonder that people get from 0.47 to 0.62 for the proportion of null, meaning that there were about a third to more than half of the genes that were involved in the difference between these two. I don't think that any biologist will believe that so many genes are involved in the process. So the point is that these methods, in a way, the things that rely on methods that rely on the center of the distribution, and later even try to estimate it. And again, the methods EM and so on, they will rely on the center of the distribution more than on the tails. I think there are should be, or how should I say it? You should be very careful with the results of these methods. And I am not sure that we can rely that much on their conclusions, especially because of that. And I don't see a remedy for that. I agree with the other methods, but I think that this fifth method, sometimes half of the genes are being dropped. I mean, that's something that really puts a big question mark. And the next thing I will refer to more to the issue that the Benjamini-Hochberg method breaks down. I don't think that's the case, and I'll case of dependency.
I should say that was Efron's.
I know. I told that Efron.
I'm not hiding by Efron, but I mean to say
fact,
I'm happy to go along with him. But I mean, yeah.
Further questions? Okay.
Are there differential expression data sets where the objective truth is known, so that
Yeah.
you could, I mean, have people tried to, or even make some of these?
I think there are some spiking experiments.
That's what I was thinking. Yeah.
I don't, because there were certainly some spiking experiments done a long time ago.
Mm.
But whether it was anything, the trouble about that is, it's too idealized situation. You would like someone to,
Some
you know,
the distribution of different.
yeah, they've
expression
taken
and
proper
so on.
samples and then they've spiked in later and stuff like that.
I know one experiment like that, but they haven't.
I certainly at the start of doing these analyses, but it's probably 10 years ago, people would have done spiking experiments, but it'd be quite useful for someone to generate spiking experiments for this sort of setting.
Yeah,
Yeah.
exactly.
Does anybody know of spikings? You know, does anybody?
Yeah, there are at least there is a Cho that produced in the 2006 spiking experiment with about 3,000 genes spiking at different level. But I use it at least for a certain level. It's done on the Drosophila Affymetric chips. But I would say it's not so nice as the real spiking when you take each transcript and you spike it in your experiment, like the Affymetric Latin square experiment. So those are, if you are looking for the quality of the data that you are using for normalizing and this kind of study, those are the best one. But for the identification of differential expressed gene, for sure there are too little differential genes inside. And the Cho data set is much better, but the quality of the experiment is very limited. It's only triplicates, and is really, you want to have an idea of what is going on, you need much more replicates, even in this field.
Welcome.
Can I ask sort of a question of the biologist also in this regard, which is, I mean, so this data set is a data set which has been examined now for about 5 or 6 years, this head-to-fork data set. Now, is there any information which is coming from outside this experiment which would substantiate or not substantiate some of the conclusions that have been drawn? In other words, genes or interactions which have been sort sort of validate it on some other grounds? Is that at all possible? Other than what you see from these microarrays?
I mean, but I think that there could be, but I think it's one of these very open areas, because trying to use this classification where you're trying to help, it's one of those situations where people genuinely don't really understand the biology, so it's hard to necessarily come back and say, oh, well, that agrees with our prejudice. I would say, roughly speaking.
Yeah, we do lots of RT-PCR validations on our experiments, and so we're lucky to see sort of per experiment sort of 20% overlap.
I mean, it would be.
Whatever.
I don't know. Well, one thing to be aware of is that I think there's a feeling that, well, I don't know. This is a longer beer conversation about whether all of these technologies will slowly get replaced by sequencing instead of anthropometric shows. They probably won't be in the short term, but they may be in the long term. And then, but a set of really nice gold standard spiking experiments would be good. Wolfgang, does somebody keep them somewhere, like in Array Express? I mean, is there a little tag that says?
There's a couple, but they are distributed all over the place.
And they're not kind of grouped together as a nice little, here are the spiking experiments, and
Seems like a help.
that would help, wouldn't
Yeah,
it?
yeah.
Wouldn't that be a useful thing, just to say, here are all the spiking experiments for you to go off and do it, and these are the results. These are what you should be going for. That would be a useful thing to do.
Raphael did this for Affymetrics, but it's also platform dependent.
Yeah.
But there's many, I mean, innovators relates to the question that we had before on the periodic genes, which is in the end a similar question to identifying differential expressed genes. And
What's the
there,
gold standard? Yeah.
and there, for example, there's even subtle interactions between normalization and finding periodicity. Because if you get the normalization wrong a little bit, in a periodic way,
Yeah.
eventually everything will look periodic. So there are many also loops and feedback circuits that have to do with pre-processing of the data, which makes these questions in the end often very technology dependent.
I think we have to close off the discussion. Thank you again.